I'm Ben Finkbeiner. So I'm here to tell you that there's one topic that's even more interesting than verification, and that is synthesis. So I'll tell you all about it starting tomorrow. But so I was asked to select one really interesting paper from this area, and I chose one from 1990 by Amir Pneli and Roni Rosner. That is actually a pretty depressing paper in a way, because it says that what we're trying to do here is really hard, if not impossible. But there is no impossible, right? So this is an interesting challenge. So first of all, synthesis means that we start with a specification and we try to generate a implementation that is guaranteed to satisfy the specification. So compared to verification, we get the same end result, namely an implementation that is correct, but we bypass the manual writing of that implementation. We try to generate it from the specification. And this obviously doesn't work all the time, because it could be that there simply is no implementation. So a potential result is that you say the specification is unrealizable. But if it is realizable, then you want to generate an implementation automatically. So this problem is really old. It arguably got started with Alonzo Church in the 1950s. And Church's challenge triggered a lot of interesting research, where plenty of papers could have been chosen for this. So Church's original notes are fascinating. The first solutions by Büchi, Landweber, and Rabin would have been adequate choices. But what I'm going to do is skip ahead sort of into the second wave of research into the synthesis problem. So this was the first wave ignited by Church's work. The second wave came later with the advent of the temporal logics. And here I'm going to zoom into this work by Pneli and Rosner, where they looked at a variation of the synthesis problem that looks like this. So not only do we have a specification, but we also have a target architecture of the system that we want to build. So the key difference is that we're not building a single component that realizes the specification, but rather a network of components that communicate according to certain restrictions. Now, let me quickly argue why this is such an interesting problem. So, I hope you can see this. So this is a really simple synthesis problem. I have one component that has input and output, and my specification, this is an LTL formula, it says that globally input if and only if next output. So in other words, I'm building a component that communicates whatever it receives as input a little bit later as its output. Now obviously this specification is realizable, and it actually stays realizable if I use an architecture consisting of two components. So I again have the input and the output, but now the first component gets the input and the second component produces the output, and they are communicating through a channel C. Now I can still realize this specification. The first component just passes on whatever input it receives, and then the second component does the output. But note that now we depend on this channel. If for some reason that channel isn't enough to communicate all this information, then it can't be done anymore. And in particular, if my specification restricts what is allowed to happen on that channel. For example, here this specification says that the channel always contains the value false, then this can't be done anymore, right? Because there's no way for the first component to communicate the input it receives to the second component. So now this becomes unrealizable, and the reason is that the second component doesn't have enough information to do its job. So as I said, the paper is a little bit depressing. So the key result is this is undecidable. There's also good news. For some restrictions on the architectures, namely that they're hierarchical, this is decidable.
But maybe you can make it in context. So for people like me who are outside the field, in the case of finite state machine, like sequential problem, is it decidable?
So I'm not sure I understand your question. The question was, yeah?
Instead of here you have the thing that you have is undecidable in the distributed state.
Yes.
So if I restrict that, so it's just I have a single node.
Oh yes. So the question was, if I just have a single component, then indeed realizability from LTL is decidable. Yes. And we'll talk about that in detail tomorrow. So the bad news is, in general, you can't do it for arbitrary architectures. And the good news is for certain architectures, and the one component architecture would actually be a special case of that. But essentially, if you have a pipeline, so a linear order on the components, then it is decidable. But I should immediately qualify that it's decidable in time non-elementary. So it's arguable if that constitutes good news. It certainly constitutes an interesting challenge. Now, even the undecidability result is exciting, not only for the fact that we have another undecidable problem, but the undecidability proof, I think, is intriguing. So the proof is that for this particular architecture, consisting of two components that don't talk to each other, we can reduce the halting problem of a deterministic Turing machine to the realizability problem of a LTL specification. Now, at first sight, this sounds completely unbelievable, because we know that LTL formulas can be translated into finite state automata. So LTL is even less expressive than finite state omega automata. So how could you possibly reduce the halting problem of a Turing machine? And the observation is that under incomplete information, LTL is actually, in some sense, as powerful as a Turing machine. So the proof goes like this. These inputs to the two components are simply starting signals. So you want to force the two components to implement a given Turing machine, and the input just says, go ahead and output a configuration. The output of the two components are then sequences of configurations of that Turing machine. So if we accomplish this, then obviously we can specify eventually halt and encode the halting problem of the Turing machine. Yes? Yes, you're absolutely right. I'm not precise here. I'll get back to it in 2 minutes. The question was, what do I mean by incomplete information? So the short answer is, I mean by that component 1 cannot observe the input to component 0. Component 0 cannot observe the input to component 1. So each of them needs to act on an incomplete information, namely the information limited to its own inputs. All right. So the idea is that we force the two components to implement Turing machines, and we start these Turing machines through start signals that come from their respective inputs. Now, the big question, of course, is how would you prevent an implementation here from cheating? Because I might be able to specify that the first configuration is the initial configuration of a Turing machine, but how on earth should I specify in LTL that successive configurations are actually successive configurations according to the rules of the Turing machine? Because the configurations will become arbitrarily large, and I would need to compare positions in successive configurations, thus going an unbounded number of steps into the future. Now, the ingenious trick here is you have two copies available, and because there are two processes that you both force to implement a Turing machine, and there is no reason that they should be running in synchrony. So what you do is you let one of them start earlier, so that one Turing machine outputs a configuration, and the other outputs the previous configuration of the same Turing machine. And in that way, I see the two configurations side by side, and then I can compare the respective positions in successive configurations. Now, obviously, if the components knew what I was doing, they would cheat again, because then they might just output two configurations that happen to be successors of each other. But the point is, they don't know that, because they don't see each other's inputs. So they don't know who's the process that's ahead, right? And therefore, they can't cheat, because I would find a constellation in which I would find out that one of them cheated first. All right. So the message here is, because they don't know each other's input, they have to do a much more powerful job than you would expect. Even though I'm only checking them with a finite state device, they are forced to implement an infinite state Turing machine. All right. So the question that you may have on your mind now is, yes? Oh, sorry. Yes.
Is there like a common clock or a cycle?
Yes. The question is there a common clock? And yes, in this model, we're assumed to be synchronous. So in each point in time, in this case, both components make a step, and my LTL formula refers. The notion of time in the LTL formula refers to this common clock. Yes, please.
I don't exactly get the idea of they might be cheating. In principle, they are supposed to simulate a Turing machine.
Okay.
In what sense they are malicious?
Very good question. So will do. So the question is, what do I mean by cheating here, right? Because what does it mean to cheat? So remember, the problem we're solving is we're looking for an implementation that satisfies an LTL formula. So all I know about my implementations is that they do satisfy this LTL formula. My intention is to force them to implement a Turing machine. And by cheating, I mean that they somehow manage to realize my LTL formula without implementing the Turing machine, right? So, for example, if they knew the sequence of inputs from both components, then they could just wait until I start comparing the configurations, and then the first component would output one configuration, let's say the initial configuration, and the second component would output the successor configuration of the initial configuration, and they would just keep doing that, right? So the whole trick here is that they don't know who's ahead, and therefore who needs to output the successor configuration, and who needs to output the earlier configuration. So the argument why this is actually the sequence of configurations of a Turing machine is that my specification says start by outputting the initial configuration, and then I can, by induction, show that the n plus first configuration is actually the successor configuration of the nth configuration in both components.
It would help if you explain how they would implement this specification if the machine does terminate.
Okay. Moshe's comment is, I should say, what the implementation looks like if the Turing machine actually terminates. Well then, in that case, the Turing machine has a finite sequence of configurations upon which the last configuration contains the halting state of the Turing machine. So it's a finite sequence of outputs that needs to be produced. So I could build a finite state automaton that just goes through these finite positions of the sequence and outputs them. So that means if the Turing machine halts, then there exists a finite state implementation that demonstrates that, namely a finite automaton that outputs exactly the sequence of configurations. If it doesn't halt, then such a thing doesn't exist. All right. So the question here, of course, is, does that mean that the problem can't be solved? Oh, there's another question. Okay, so the observation was if the Turing machine doesn't terminate, then there might still exist a finite state automaton that produces its sequence of configurations. Maybe the Turing machine is simple enough that it doesn't need more than finite memory. But of course, my specification contains the statement eventually halt. So it requires that this sequence eventually reaches the halting state, which obviously wouldn't be reachable if the Turing machine doesn't halt and the implementation here produces the actual sequence of configurations of the Turing machine. All right? If there are no further questions, no, there are further questions.
For example, original search problem was given a specification, is a system realizable?
Yes.
And then it was proven that if it's realizable, it is realizable by finite state automaton. Yes? And specification you describe it is always realizable. Doesn't matter. What is your specification?
Okay.
So it is realizable.
So the comment is, isn't the specification here always realizable? And the answer is no. It's realizable if and only if the Turing machine halts.
So what is your specification?
My specification says, is such that it enforces that the two components output the successive configurations of the Turing machine, and these configurations reach the halting state.
So somehow I'm still confused. So the reduction used the power of LTL to denote the successive states.
Okay.
To compare states.
Yeah. So this is, the question was, what does the LTL specification actually do? And my point was, naively, you would expect that it does this, that it looks at one configuration and its successor and makes sure that this is legal, meaning that none of the positions except where the head of the Turing machine is changes, right? So the tape stays the same, and at the position of the head, the prescribed change of the Turing machine happens, and the new position of the head is where the Turing machine says it should be, right? And what I said here is this can't be done because the configurations are arbitrarily long, and I would need an infinite number of next statements to cover all these cases. I can't do that in a finite formula. But what I can do is compare the configurations if they happen to be lined up side by side. Because then I don't need to look far into the future because I see corresponding positions of the two configurations at the same time. So the only thing I need to say in my LTL formula is that the new position of the head is either at the same position or at the previous or next position, which I can do with just one next operator, and that the corresponding positions of the configurations are either the same or have changed according to the laws of the Turing machine. So if I manage to see the successor configurations side by side, then I can indeed specify in LTL that they correspond to the next configuration relationship of the Turing machine. What I have to do is actually make sure that I can align the configurations accordingly, and that I do with the help of this start signal. I just let one of the machines start later so that it will produce the configuration with just the right amount of delay so that I can compare them side by side. All right, so don't be depressed even though it looks like distributed synthesis can't be done. Stay tuned. Thank you.
Das heißt irgendwas mit Pedal.
Okay. Ich habe keinen USB-Anschluss.
Ach so. Okay. Okay, then I take my laptop.
No, there is the laptop here.
Well, there is one. Look, there's one here.
Yeah, there's the laptop here. Let's see if we can connect it somehow.
thought this is super clever, but
USB.
Okay.
Can you open the USB?
pedal.
Which one? This one?
Yeah. This, okay, looks good.
You want presentation?
It, and I would use this one if this is.
Ah, okay.
This is better.
The one here. Should work.
Yeah, seems to work. Thank you.
Thank you. So now the second one is Christel from the University of Dresden.
Yeah.
And she will tell us about something completely different but related about distributed system and but also probabilistic, right?
Yeah, yeah. Well, this fits very well to the end of my lecture in the morning, and indeed, Moshe interrupted me or prevented me to show you one more slide, and now it comes now. Well, I have been asked which classical paper has influenced or changed your life. Well, that's a very difficult question. But this one is the complexity of probabilistic verification by Kostas Kokobetes and Mihalis Yannakakis is certainly one which is very important for my life, yeah. Well, and just to mention this, it appeared in Journal of the ACM in '95, but the results are a bit older, so the full paper relies on results that has been presented at Fox 88. Well, if I looked again what is stated in the paper, what are the main contributions and what the author states themselves is two parts. One part is about Markov chain, what they called sequential probabilistic programs, and what they showed or what they considered was the LTL model checking problem. So you are given a finite state Markov chain plus an LTL formula, and the task is to compute the probability for phi. And what they proved was this is solvable in exponential time. And the other main contribution, according to what they list in their introduction, is for Markov decision processes. They called them concurrent probabilistic programs, so that's a model. We will talk later about it, where we have probabilism plus non-determinism. And here they considered the qualitative LTL model checking problem, which is now a decision problem, where the task is to check whether the minimal probability for phi is 1, which means this minimum is taken over all the possible resolutions of the non-determinism. So even in worst case scenarios, the formula should hold this probability 1. And here they prove double exponential time completeness. Now that's what they state in their intro. These are the main contributions, but indeed the paper is long and it contains many other interesting things. Let me first come back to the, first for the Markov chains. This morning I ended, this was the slide next to the last one. So this schema, a Markov chain, and we translate a PCTL star formula into an LTL formula, then a deterministic automaton, and then we combine them into a product Markov chain. And I mentioned that this step here, if you have the product, then what you have to do is a graph analysis plus linear equation system. So this step is not the expensive one, or let's say it runs in time polynomial in the size of the product. But indeed, this product can get very huge because the size of this A can get huge, and the expensive step is sitting here. So altogether, this procedure has double exponential time complexity. But from a complexity theoretic point of view, this is not optimal, and this is one of the results of the Kokobetes-Yannakakis paper. And this was the slide this morning I wanted to mention. So let's say that the algorithm I've shown you has double exponential time complexity. But there are nowadays several single exponential time algorithms, and the Kourkoubétis-Yannakakis algorithm, at least to my knowledge, was the first, and it doesn't use automata at all. It uses an iterative approach. I come back to this in a second. And in the meantime, there have been several other algorithms, automata-based, that also can achieve the single exponential time. One of them, is by, I forgot the first name, Bustan. What is the first name? Doron, okay. Sasha, I think, and Moshe. They went from LTL to weak alternating automata, and maybe you disagree, I would say you do some kind of power set construction on the alternating automata. And another approach was to use a very strong form of unambiguous Bücher automata. This separated means that whenever you have two states in the automata, then their languages are disjoint. And indeed, the very, very old algorithms from LTL to NBA, they enjoy this property. Well, the very old. They guarantee this property, but then you get also a single exponential time algorithm. But in practice, it is somehow clear that these constructions cannot compete with other more clever constructions. And we are not aware that any other algorithm from LTL that generates a separated Bücher automaton is known. At least I've never heard about it. And more recently, this result was generalized for the full class of unambiguous Bücher automaton, and this step also needs, let's say, some of the LTL algorithms, LTL to NBA algorithms, can be adapted to get, in a fairly simple way, an unambiguous non-deterministic Bücher automaton. Okay, so this one here in the paper I picked as the one that influenced my life was, at least to my knowledge, the first one. Well, what it doesn't work with automata at all. It relies on an iterative approach, so it starts with a Markov chain and the LTL formula, and then, so this is the M and the phi, the original one, and then it generates a sequence of pairs, a new Markov chain plus a new LTL formula. And these, for one such step, from phi to phi 1 or phi 0 to phi 1, it picks one of the innerst temporal operators and replaces this sub-formula, so be it a next A or A until B, and replaces it with a fresh atomic proposition. And at the same time, it modifies the Markov chain by adding one bit to each state, and the intuitive meaning is whether, let's say, the part of that state that satisfies this particular sub-formula or not. I find this algorithm very, very tricky. So the bound that one can guarantee is that so for each step the Markov chain at most doubles concerning the number of states, and the formulas, they get simpler, and in the end, for the algorithm terminates as soon as a propositional formula has been generated, in which case the probability for that formula in this obtained Markov chain MK can be simply obtained by looking for the initial states and computing the weight where this formula holds. Yeah, well, and what is proven in the paper is that this chain, along this chain, this is probability preserving, which means that the result that one gets for the final Markov chain indeed gives the wanted value. Well, and this paper contains several other results, and just to mention some more, it uses these ideas. Well, this one has exponential time complexity, and it explains how to modify this algorithm to guarantee a polynomial space bound for the decision problem where the task is to check whether phi holds with probability 1 in M. And this gives the membership to p-space and p-space hardness was already known at that time, again by a paper by Moshe. And it also considers the case where the starting point is not an LTL formula, but the starting point is a non-deterministic Bücher automaton, and addresses the problem to check whether either almost all words in the Markov chain are accepted by the NBA, or the probabilistic emptiness problem, which means that almost no word is accepted. And speaking roughly, what they show is the very naive power set construction that you know from non-deterministic finite automaton. It can be applied, but of course it needs some careful notion of recurrent state and a strongly connected component analysis in some kind of product to achieve this single exponential time algorithm. What I found, and when I read first these results, I didn't believe. I started to try to find counterexamples, but I failed. I think what they did was sorry?
Why? What made you?
Let's say because this is a standard power set construction, and they start with a Bücher automaton, and so what is known is that the standard power set construction cannot determinize a non-deterministic Bücher automaton. It needs extra things. And they do not claim that this automaton accepts the same language. They even do not consider it as an automaton. But they, let's say, they use this somehow in a very clever way.
So where is the clever thing? The algorithm or the reduction? What's the so?
Let's say this is not a proper reduction. They call it a table, and they do the standard determinization there, and then they define what are recurrent states. Well, these are states belonging to a strongly connected component, from which on in the power set construction you can go back to that state.
It's a bit of a magical paper.
Yeah.
In the sense that it says, here is the algorithm, here is the proof that it's correct.
Yeah.
It is correct. You read it and the proof is correct, and you have no idea why it's wrong.
Yeah. So I'm
You read
glad
it
to.
many times and you say it's hard to believe.
Yeah, so I know this must be wrong. This was my first reaction. But I believe it is correct. So. Well, and there is a detailed proof. But
Exactly believe.
sorry?
Exactly believe. You said, I believe.
Yeah. Yeah. And now for the concurrent case, this means the case of they didn't use this word Markov decision process, a model with non-determinism, and they called it concurrent because the purpose was to represent interleaving. There, as I mentioned before, they consider this decision problem to decide whether even under worst case scenarios, the probability 1 can be guaranteed. Which means the formula phi holds almost surely no matter which interleaving is chosen. And what they show is they present an algorithm that runs in double exponential time, and here again they rely on results presented in Moshe's Fox paper and the Lix paper 1 year later together with Pierre Volpaire. And speaking roughly, the steps are as follows. We start with the formula phi, we consider its negation, and then that's what they use as a black box schema to generate an NBA of possibly exponential size. And then they describe a transformation of A into another NBA called B here, which is equivalent, so it accepts the same language, and which is deterministic in the limit. This means not the classical determinism condition, but whenever you consider consider the fragment of the automaton that is reachable from some accepting state, then this fragment must be deterministic. So as soon as you entered, or the automaton entered an accepting state from then on the behavior is deterministic. Unambiguity. Yeah, well, in this, how to reach an accepting state, you can still have several passes. So they do not need to be unambiguous.
Can you repeat it?
Sorry,
It's the same to be semi-deterministic justified name. Some people also call it semi-deterministic.
To be honest,
This is not semantic ambiguity. This is
No,
deterministic
I'm
in the
saying
limit.
I'm
No,
not
it's
saying
talking about
semi-deterministic.
see,
Ah,
to be honest, I
you
don't.
know the term semantic.
Me neither. That's why I can't answer. I'm sorry.
Some authors use them interchangeably for ambiguous or limited.
Okay, okay. Then the answer is yes. I simply never heard about this.
Semi-deterministic is equivalent deterministic in the limit, then the answer is yes.
Okay.
If it is not, then the answer is no. Just comment on this. This is exactly the proof in the 85 paper,
Yeah.
but my step 2 was incorrect.
Okay.
So everything I followed, this is the scheme exactly what I used, but my construction from of step 2 was incorrect,
Okay.
and they came up with a correct implementation of that construction.
Yeah. Yeah. Well, then
So
this.
everybody wants to know. I discovered the error the night before I was supposed to give the talk.
You didn't commit suicide? Come on.
Well, and then.
It was a long night.
Yeah. And did you tell it in the talk?
I was giving the first talk in the morning, and I said, "Here is the proof. Here is the Bible."
Full disclosure.
Well, but I find the construction they present is also comparably simple. So it relies
Very
on
simple.
somehow two power set constructions, two parallel, so something like this. Well, and then the final step is again they consider then a product which is, they call it just table. They do not consider it as a Markov chain or Markov decision process anymore. And then they do some analysis of strongly connected components. Well, and they also, this was the membership to 2x time and 2x time hardness. They present a reduction from the membership problem of exponentially space-bounded alternating Turing machines. I did not present here a sketch of the proof, and to be honest, I couldn't. Well, so altogether, if I'm allowed to mention 3 papers instead of 1, then I would say these ones changed my life.
Thank you very much. Could you explain a bit, if you can, how it changes your life? If you are allowed.
Well, I find the problems fascinating. I find, let's say, there were many questions that were open, so changed my life. Well, for instance,
So,
I meant.
yeah, I know that
So for
published
instance, I was, well, this having seen these results, and I think it was also Javier once who, well, this must be possible with unambiguous Bücher Automata. I think you asked me once this.
Did I?
I think
Sure,
so.
that it was a good idea, then I did it. So
Let's say there were many questions which were still open, but let's say that's the close picture what these papers give, but inspired many directions. That's
One comment about I think of the significance of this sequence of paper. You notice the big gap between 88
yeah.
and then 2004.
This one was
or
first.
2003. So like
Yeah.
what is it, 15 years.
Yeah.
Well,
Ah.
the thing is that this 88 paper, the appeared in Journal 95, that algorithm is so magical,
Yeah.
and that there was a question was, is there anything to LTL other than automata? So kind of before that, somehow
Yeah.
people said, well, LTL, first of all, constrain to automata, and then you're done. You don't need to deal with LTL anymore. This algorithm does not use automata. It's very syntax driven. And so it looked like there might be something else to LTL other than translating it to automata. And eventually this paper showed, no, you just have to have somewhat richer automata theory. But the question still exists. Is there anything to it other than that you cannot do with automata? And so far the answer is empirically, no, everything you can do with LTL,
Yeah.
you can do
Yeah.
with automata, but it takes sometimes non-trivial work. It just takes some time to come up with these ideas.
Yeah. Well, and another comment, I'm not aware of any implementation of this algorithm. Indeed, one student in my group just started. If someone knows, I'm not aware that this one has ever been
Actually,
implemented.
It looks like, from looking in the paper, it looks like it is implemented.
Yeah, well, it's not so.
Almost like
Yeah.
dynamic programming or
And
some other iterative method that you can use.
I'm Moshe, you should know. Well, we asked Sasha, and he told me that there is no implementation around. Okay, this.
I don't know if any of these have been actually implemented.
So only yours?
Well, this one we implemented it. Yeah.
No question? Thank you very much, Peter.
טוב. אני just.
Okay.
קיבלתי את הזה.
אחד ישן, רצו לחבר אותי עם משהו חדש, זה לא עבד.
זה לא עזר לך? הנה, יש פה, יסתדר. בסדר? רגע, יש לך את ה... רגע, את מחוברת לרמקול? איפה?
לא.
שמה אותו איפשהו.
היא בטח היא שמה את זה שלקחה. הנה זה פה.
תודה.
צריך גם עכשיו?
כן, זה שומעים.
כדאי שתשימי כן מקליט.
Okay, this paper didn't change my life, but it gave me a lot of pleasure and some inspiring inspiration that I'm using even to these days. So the name of the paper is already a little bit strange. It's called Sometimes and Not Never Revisited. On branching versus linear time temporal logic, and it was written by Alan Emerson, who is a kind of guru on temporal logics and automata. Some years ago, there was a handbook in theoretical computer science. It was excellent, and there was one chapter on temporal logic by Emerson and another chapter by Wolfgang Thomas on automata, which were invaluable. Everything that was known by then, it was 20 years ago, was there, very concise, very organized. So this is the person that did this job. So, and the time it was published in the 85 in JACM, is one of the most established journals, and appeared 3 years before in POPL, in a conference on programming languages. And there are, I would say that there are two contributions that the paper consists of. The first one it has a long and very thorough debate with another paper by Lamport. The other paper by Lamport was titled "Sometimes is Sometimes Not Never" on the temporal logic of programs. So you see that they both play on sometimes and not never. And actually, the goal was the goal of this paper, and then also the goal of the paper I'm talking about, was to compare the expressive power of logic. And what this paper, what Emerson and Halpern paper claim about this is that they try to compare, as Moshe seems to likes to say, apples and oranges. So they compare the expressive power of linear temporal logic and branching time temporal logic, specifically LTL and CTL, but also others, in a way that didn't put them on the same ground. And therefore, the results were really strange. They were correct, but they were not proving the way it should. So the Emerson-Halpern paper first makes clarify the problem. Then it suggested a solution, and the solution was the definition of this CTL star logic, which combines CTL, the branching time logic CTL, with the LTL, which is the linear time logic, and it's actually more expressive than the two logic, and it actually gives a unifying approach to present many logics in the same framework as sub-logics of CTL star. And then the expressive power it was possible to compare the expressive power on a very basic foundation. And finally, a great part of the paper is actually comparing the expressive power of all kinds of sub-languages, in particular LTL and CTL, and many other sub-logic that are not of particularly interest because we are not using them as is. This I mentioned already, at least at the in the morning. Temporal logics were suggested very early by logicians and philosophers, and the book presenting what was known about temporal logic was written in 57, a long time ago.
It was tense logic, not temporal logic.
Okay, but still it was referring to time. Okay, yep. And as I mentioned, they considered linear time and branching time. Then Pnueli suggested to use temporal logic as a specification language for reactive systems. And originally, the original papers suggest to use linear time. But later on, Pnueli and friends, Ben-Ari and Mana, suggested also to use branching time and actually defined it. And then there was, okay, just to recall something from the morning, when I talk about branching time, I consider the whole computation tree, and then when I'm in a state, I can refer to all paths, or there exists a path leaving a certain state. And on the other hand, with linear time, I just see one computation at a time. And there was more than 10 years of infinite debate between the supporters of linear time and the supporters of branching time. For instance, there is a continuation to this paper of a paper, branching time strikes back. So, and so on and so forth. It was really fierceful. And at some point, people calmed down and they saw that it's a matter of taste and it's not such a big issue. And for some implementation, some application like model checking, maybe CTL is better in some situation and LTL is better in others. And there were again a lot of work that show you had something about LTL better in CTL in some context, you and Orna. About when it's, I don't know, it was,
Showdown. They had the showdown, the final showdown.
Aha, never mind. So what Lamport tried to do, he defined kind of Kripke structure, but a little bit different. It included a set of states and a set of paths over states. So he didn't have the transition relation, but just the set of paths. And the labeling of the path, which identify for each state which atomic propositions are true in the state. And then he defines a set of temporal operators. I call them by name because I didn't know to draw this very strange drawing. So there is, one is called always, it's the box. And it's like globally, more or less. The other one is sometimes, and it's like eventually, the spirit of it. And then it's easy to see that if we take not always, not F, it's actually like eventually F, because it's not true that not F holds forever. So at some point, F should hold, and he calls it not never. And then he compares sometimes and not never, and this is the origin of the title of the paper, that sometimes not never is sometimes not never, or whatever, some combination. So what he did, he gave two kind of interpretations for these operators. So one viewed this always or sometimes or not never over branching time interpretation, and then it actually take a state and interpret this formula over a state. So for instance, if we say always F with respect to branching time, then the meaning was that F should hold along every path globally in every state F should hold. And the sometimes on the branching time is interpreted as along every path eventually it should be F here. So you see that even though these are only temporal operators, here the for all paths just sneak in without any syntactic notion to refer to. On the other hand, if it takes exactly the same formulas and interpret them over linear interpretation, you see that they always just became globally F, the A just was dropped, and for eventually, the sometimes is translated to eventually F. So sometimes in the future F should hold. And now it is easy to see that sometimes is always equivalent to not never, just by putting not. For the linear time interpretation, but they are not equivalent over the branching time because we have AG, and the negation of AG should be there exists a path along which eventually F holds, but here we don't have any notion of exist a path. So this was the kind of mismatch that they just, he didn't see that he compares two different things, and they cannot be compared because they are over different interpretation. So based on Lamport definition, he showed that branching time and linear time have different expressive power. And what Emerson and Halpern said, that based on his definitions, his proof is correct. But they claim that his definitions are not correct, because he tries to put things on a different ground and then compare them, and it doesn't make sense. So they claim that a unified framework is needed, and they provide it. So what they do, they suggest CTL star. This is actually was a new invention, and CTL star has all the combination of atomic propositions for every path. There exists a path, we didn't exist before, and all these temporal operators, and this actually it's not, it doesn't add more expressive power. This says that something holds infinitely often, and this says that from a certain point on something holds, and then they interpret, okay, they give an inductive definition of the semantics of CTL for state formulas. They were interpreted over states. For path formulas, that they interpreted it over paths, but they all needed to be eventually state formula. So what happened is that path formulas were only some sub-definition in the inductive definition, but they were not the goal. All the formulas, the CTL star formulas, became state formulas. And now, since we had this uniform, uniform, where is it?
Okay.
Ah, okay, uniform. I'll erase it later, if I have an eraser. So once we have this uniform semantics, we can compare it. And they also show that LTL and CTL have different expressive power, but they do it correctly. And what I like about the paper, just a moment, let's see. Okay. What I like about the paper is that actually, for the first time, it gave some uniform semantics, which we all use it. And it's trivial now that if you want to refer to CTL or LTL or CTL star, you have to use the same interpretation so that you can compare them correctly. All this debate and the definitions that were very hard at that point, now they are trivial. They are just the way we treat things. So they were the first to say this is how it should be done, and I think it's beautiful.
So you said that earlier, Mana and they introduced
Only LTL actually.
no, but they don't.
In the branching,
Yeah. So they didn't have this kind of definition.
I actually don't remember the semantics of Ben-Ari and Mana and Pnueli. I didn't look at it now, so.
No.
So this made things very clear, very well defined, and it's nice. I think it's nice that at some point, if we teach now temporal logic, we take this semantics and we teach it, and it's clear that this is the way it should be done. And then for more than 10 years, people didn't know what should be done. It's interesting to know that knowledge accumulates gradually, and at some point it's so clear that this is the way and everyone knows it and so on. But It took a while to understand more and more and more. So this is the beauty of the paper in my view. And in addition, the proof that CTL and LTL are incomparable, it's a beautiful proof and quite involved, especially for that there is a formula of LTL that is not expressible in CTL. The other direction is relatively simple. It defines a sequence of recursive structures, and I even teach it in my verification course because I think it's beautiful. Okay. Sorry?
I understand comparing languages, but what does it mean to compare a formula to another formula?
So we compare, we just want it to be equivalent. So if we say the two languages are incomparable, it means that there is one formula in one logic that has no equivalent formula in the other logic. And equivalence means that if it's a state formula, then for every structure and every state, the value of one formula should be identical to the value of the other one.
But what do you mean when you say that the state formula cannot be compared to a cat formula?
Oh, this was more on a more intuitive level. It means that in order to show equivalence between two formulas, this was the goal. We need to have a common interpretation, because if you interpret one formula on one model and then another one on another model, then you don't have a notion of equivalence.
Okay,
So this is what I meant. That
Go back to your
it refuses. I wanted.
so is it roughly that the cat formula is like linear time and the state formula is like the branching time in one-point statement?
Yes. אולי פתחתי אותו מהר מדי. אוקיי. Okay, so this one or the one before?
So really, this is a bit misleading because, as you pointed out, LTL are path formulas, CTL are states formulas, so they are.
So what this paper? Okay, so
Really
what?
you meant is when you consider both as fragments of CTL star.
Exactly.
then
So what they did?
turn LTL into view it as a state formula.
Yes.
That's
So
what
yeah. So what Emerson and Halpern did, they said we will refer to LTL formulas as sub formulas of CTL star, and now. Great. And now if we have some path formula which is from LTL, we refer to it as for all paths, this formula should hold. And now we can check it over a state. And anyway, when we say we refer to LTL with respect to a structure, when we say that the structure should satisfy A, we anyway wanted to say that every sequence, every path of M should satisfy phi, or in other words, M should satisfy A phi. So they just took whatever was accepted at that time, and they put the A in front syntactically. And now you can interpret LTL formulas over states and compare them to branching time logics which are also interpreted over states. Yeah?
With you, you just add a universal quantifier to
Yeah.
then I expect the negation to exist.
Yes, but for LTL, the exist is not part of the language.
Exactly. So this is my question. How is this handled?
So it's not, LTL is not close to negation. So in principle, what we do, for instance, when we check, when we apply model checking, we want to check whether M satisfies some formula phi. So we, oh, this is confusing. We construct an automaton. This is what I guess Javier is going to talk about. We construct an automaton for not phi. And the automaton accepts all behaviors that satisfy not phi. And now we check whether the intersection of M with the set of all paths that satisfy not phi is empty. So we don't say that not phi on top of this, that E not phi is an LTL, but we go this way using automata that actually implicitly use the negation.
I think I can remark. You defined several logic, but you have not defined what is a temporal logic. Most of the
I did it in the morning. No, I didn't do it fully. I have many slides, but what do you mean?
So what is a temporal logic?
May I ask a related question?
Okay.
Thank you very much for recording debates in 80s about which logic is the most correct, the most right logic. But also at this time people suggested dynamic logic.
Yes.
Why not dynamic logic? Why temporal logic overtake? Overtook? What, of course, it is a question of taste. But
Yeah.
dynamic logic, well.
I actually don't know. David Harel will be there in 2 days and you can ask him. But I don't know of any model checking that were developed for dynamic logic. So why
For compositional dynamic logic, yeah.
there are model checking? Actually, the formulas include part of the program in it. And I don't know. You know, sometimes it's a matter of luck. So for instance, yeah, test or luck for the certain formalism. So for instance, for many years, CTL was the best for model checking. And maybe the reason is that the people that developed CTL model checker were more forceful. They are more insisting on pushing model checking forward, and they had tools, and therefore these tools got into industry, and it became very very popular. But sometimes it's
maybe another possible answer is that PDL was a fragment of the modal mu calculus. And then the modal mu calculus was also quite popular at some point, and then PDL was in between, right? So if you wanted to do theory, why not go to the modal mu calculus? It was, you could do it a bit more generally. And if you wanted to do applications, well, maybe you only need LTL. So
yeah.
I don't know, maybe it was a bit caught a bit in between. But,
so actually, mu calculus, it's very powerful, and the model checking is very straightforward. So it's fixed point, and it's easy, it's clear how to do it, but it's very difficult to write specification in mu calculus. Once the formula has two nesting of fixed point, you are lost. You don't know what it means. So I guess this is why people didn't take it as an option, a specification language.
But There is a chapter which you missed, which is what happened in the early 2000s.
In?
In the early 2000s,
Yeah.
industry decided to adopt it,
Yes.
and the debate somehow had to be re-debated,
Yeah.
and it was settled. The industry chose linear time logic. It's not LTL, but essentially.
But with extension,
the extension are lip service to politics. But in another one like SVA, PSL has still branching extension, but the next standardization dropped them completely. They're purely linear time.
this is because you were there.
No, I was in the first one. I was in the first one, not SVA. SVA I was not involved.
So Moshe was at Intel. It was actually quite nice. There was a competition between hardware specification language, and it was IBM from Haifa that suggested the language, Intel Haifa, which was then very active with the help of Moshe. And then there was Motorola that now they are completely out of market. And there was, this more like testing Vericity. Yeah, that's now Cadence. Yeah, and the chosen language was the one of IBM, but with the addition of LTL. So it was a mixture of CTL and LTL, and it's all history.
Thank you very much, Oda.
I don't have a slide, so do you think we can raise this?
Yeah, that's fine.
Otherwise, I can use the tablet.
No, that's
Okay.
רגע.
So Javier will talk about something different but related, the usage of byte protection to decide the difference between context-free games, right?
Yeah.
This?
Right.
So let's see. Okay, so let me write the title here of the paper is Decidability of by simulation equivalence for processes generating context-free languages. And the authors are three Dutch people, so actually Jos Betten, Jan Bergstra, and John Willem Klopp. And they were working at, Klopp was working at CWI in Amsterdam, and Betten and Bergstra were working at the University of Amsterdam at the time. Was it right? Yes, exactly. Okay, so this paper is probably less known than the others. And actually, I wanted to conduct here a little poll. So let's see. Who of you had already seen somewhere the paper by Pruelli and Rosner, the paper about synthesis? Doesn't mean that you have read it. Doesn't mean that you know that it existed. About, let's say, 12 people or so. What about the paper by Kourkoubetis and Giannakakis? Verification? Similar, more or less. What about the paper from Orna? Fewer people? No, it's about similar. And what about this one? Who knew about this one? A few people. You see, only 3 people. So, and I've chosen it partially for that reason, because I think that this paper deserves more recognition than it has received. It's not that doesn't mean that it has no recognition. It is, if you look at, by the way, I forgot to say the dates here. The conference paper appeared in 1987. The paper appeared then, the journal version in Journal of the ACM, again, was 1993. Okay, and it has, if you add up the number of citations, it's about 300. So it's not so little, but it's, I think it would deserve more. And I've chosen it because of that, and because it, actually, quite a few years later, when I was trying to find out where were the ideas that had influenced my research coming from, actually I ended up with this paper, even though at that time I didn't know it, or I only knew it by some reference. Okay, so then let's take this was 87, this was 93. Let's take at some point in the middle, 1990. What was the world like in 1990? So the two things that you should know about that, how many of you were born in 1990? How many were not born in 1990? Okay, about one half, right? There are two things you should know about 1990. The Soviet Union was falling apart, in particular, and there was no internet, right? In fact, at that point, that was the year in which the years in which email was starting to be widespread in universities, right? Nobody had email at home, but at universities you could have some email. The combination of the two meant that at that point you could go for a workshop somewhere in a place which was a bit hidden maybe, and then when you were coming back, the map of Europe had changed, right? It was a completely different map. Anyway, so what was happening in the verification area, or which were interesting areas of research related to the topics of this? So one of them was, of course, automatic verification. So, model checking had started in around 81, 82, the first papers, but of course it took a couple of years until things were starting to be well known. And in 1990, model checking was going through its first boom. And the reason was that at that point, this was the year, a couple of years earlier, Ken Macmillan had come up together with Ed Clark with symbolic model checking. And this was the idea of using binary decision diagrams as a data structure for model checking. There was a very influential paper at that time which was called Symbolic Model Checking 10 to the 20 states and beyond, right? Maybe some of you remember or have seen that paper. So it was, these techniques were showing for the first time that actually model checking could be really interesting for industry, right? And in particular, it was showing that you could verify interesting hardware circuits. And at that moment, things go fast. So it was the golden age of BDDs, right? And at that time, the CAF conference was only about BDDs. It was, some people were starting to criticize that and say, CAF is the BDD conference, right? This is boring. In fact, that was one of the reasons why the TACAS conference was founded. Because people were saying, well, there are more than BDDs in life, right? And some people were starting to think ahead. And okay, okay, this is now clear that the model checking is interesting for hardware. And what about software? And related to that question, what about model checking infinite state systems? Okay, because in software, you were actually finding this problem. In hardware systems, the idea is that you had your circuit with maybe your 100 Boolean variables, and well, your state space was maybe very large, but it was finite. Right? And then you could apply a number of questions were clear, like decidability of certain problems, right? But for infinite state systems, things were not so clear. So in fact, it was software. What about software? What about infinite state systems, right? So that was the atmosphere at that time. So there was another area, which was concurrency theory. And in particular, well, let's call it concurrency theory, which had started also in the beginning of the 80s with the work of Milner, Robin Milner, and also Tony Hoare. And the idea there was, okay, let's try to see if we can extend algebraic techniques, the kind of techniques that you use for dealing with equations, right, or when you are doing algebra. Let's see if we can also use that approach in order to reason or evaluate maybe let's say reason about systems in order also to prove whether they are verifiable, whether they are correct or not. Here the emphasis was not in automatic techniques, It was more about, well, how to develop methodologies. Well, eventually, of course, automation was also interesting, but it was not the primary goal. And for that, you know, Robin Milner had observed the following. Robin Milner had observed, well, if you take a parallel composition of programs which are communicating by some means, right? Well, imagine that they are communicating by messages. Then the natural notion of semantics for a program is no longer that the program is a function that gets some inputs and produces some outputs, because these are communicating processes, reactive systems. So of course the first natural idea was to say, well, let's say that the semantics of a program is just its set of executions, the set of sequences of messages that it can produce or is willing to accept. And what Robin Milner observed is that, unfortunately, that notion is not a congruence with respect to parallel composition. And what does it mean that it's not a congruence? What it means is that if you replace a program by another program which has the same language, okay, it may be the case that the parallel composition does not have the same language as the parallel composition with the new program. You know, so you replace this by something which has the same language, but then these two parallel compositions do not have the same language. And what that means is that you cannot replace equals by equals and still get something equal. This is the basic thing that you need in order to do algebra. You don't have that, you don't have anything, right? If you are not able to take a part of an expression and replace it by something equal, then you are actually, I was going to say something that you shouldn't say. Anyway, yeah, you have problems. Good. So that was the reason why Robin Milner invented bisimulation equivalence, right? Bisimulation equivalence is an equivalence notion which is a congruence under parallel composition. And he invented that notion, and this was also, again, a golden age of bisimulation equivalence and the process algebras. Actually, in 1990, this was the year in which the Concur conference, which probably many of you know, was founded. Okay, so you had this bisimulation equivalence, but you know, some people were actually these were the semanticists, and people here, for instance, were criticizing what is this good for, right? They were saying, what about the algorithmic part? And then you had a third area, which let's call it automata theory. And what was going on there? So automata theory had a first golden age in the 60s and in the 70s, right? Where context-free grammars of finite automata had provided the basis for compiler construction. Okay, so the idea was there that automata or process algebra, or context-free grammars, they were used as devices, or push and automata, they were used as devices that were recognizing which strings are correct programs and which strings are not correct programs. And there was a beautiful classical theory that we are teaching today, exactly as in those days. You know, but this has happened in the 60s and the 70s, and since then, well, the connection to applications was decaying at that point. But a few years ago, in 1990 and 86, you know, Moshe and Pierre, they had published the paper about one of the first papers about applying automata theoretic techniques to verification, and this was actually the start. This was the starting of a second golden age of automata theory, where you had a different application in which you were using automata not to describe which were syntactically correct programs, or where the words that the programs were accepting, they were related to syntax, but where you were using automata to describe the semantics of a program. Okay. So this is the landscape, and then comes this paper, and this paper lands there. And this paper, you know, at that moment, I would say this interaction was not that large, right? And what this paper did is push the boundaries here and make that interaction, that common ground among these three, much larger. Okay, and that's the first reason why I have chosen this paper, and I will tell you in a moment which influence it had. But then also my personal note, where was I in 1990? I was here, right? I had graduated in physics, so I was there, right? in 87, and in 1990 I had, well, after doing after graduating, I had started a PhD in computer science, but actually in a school of engineering, in which I was the only person who had any interest in theoretical computer science, or very little, right? So I had managed to write a thesis on Petri nets, which was part of this concurrency theory, but let's say pretty far away from these two, okay? So I was here, and then I was looking for, I was teaching theoretical computer science myself, learning from books, and hoping to find some more central topic, some topic which would be more mainstream, right? And that paper, although at that moment I didn't know, expanded this boundary so that I kind of ended up more or less there, okay? And that's why this paper was important to me. Anyway, so what is this paper doing? So far I haven't told you what this paper is doing, right? What is this paper doing? So if you remember that there is a classical result from Automata Theory telling you that language equivalence is undecidable for context-free grammars. This is a very important problem, right? Because the idea is that why would you like to have that problem decidable? Well, if you're writing a compiler, then your context-free grammar, or if you're designing a programming language, right, your design is a context-free grammar. And now, for instance, you want to optimize something, so you produce a new context-free grammar. And now what you would like to show is that actually you haven't changed the sentences or the strings which are acceptable programs, right? Maybe you have done it so that the compiler can be more efficient or things like that. So you would like to be able to automatically compare the two, but you can't. It's undecidable, okay? So what these guys did was the following. It was one of the first papers that really said, well, let's look at context-free grammars, not as something that you use to define process, to define syntax, but as a device producing behaviors. Okay, so if you want, the idea was to look at the context-free grammar in Greibach normal form, not as something like this, at saying, well, x can be right and little a and then yz, but at something like this, saying x is a process which can emit a message, which we call a, emit an a message, and then become the sequential composition of two processes, the process y and the process z. Okay? So it was a completely different way of looking at context-free grammars as devices generating behaviors. And in fact, for the people who had eyes to see it, it was very clear to see that this was actually a formal, very abstract description of programs with procedures. And in fact, the point, these three guys, they had a process algebra where the idea was precisely that, this was interpreted as sequential composition of two processes. Good. And what they did is to show that this new equivalence, which was important for concurrency theory, it was decidable. It was not like language equivalence, which was undecidable. This one was decidable. Okay, so there was hope of producing automatically being able to check whether two processes described like this, right, in this way, they had the same behaviors. So what happened then once you had this result? Well, this, as I said, allowed to move the walls. And why? Well, it was first, it gave by simulation equivalence an important push. Up to that time, this was okay, something that maybe the semanticists, they were saying that it was nice and it had good properties. Okay, but where is the hard evidence that you can do something about automation, right? Showing that this can help you where you had problems with language equivalence. This was the result telling you, okay, it's actually worthwhile looking at by simulation, right? And it is also true that, and it is also the case that when you consider this new view of classical constructions like context-free grammars, that you are able to suddenly find arithmetic solutions to problems for which until now you didn't have any. It was also having an impact in this direction. right? And the impact in this direction is that if you look at the context-free grammar from this point of view, it is an infinite state system. Okay, because you have to describe this, the states are described by sequences of variables, right? But they can have arbitrary length. So it was one of the first cases in which you could say an important verification problem, an important verification question is decidable for an infinite state, for an interesting class of infinite state systems. And a couple of years later, this was developed into, well, people started to think also, well, okay, this is one way of working with verification, to say that two things, you know, the implementation is correct with respect to the specification if the implementation and the specification are equivalent with respect to this notion. But a different way of looking at it is just doing model checking, to have your implementation and to have a temporal property and deciding whether the system satisfies the property. Well, then why don't we try to look at model checking for these kind of things, right? And actually, I was one of the persons involved in that, together with other people. And then a couple of years later, there was a paper on model checking pushed on automata. And that led to the definition of a verification theory for programs with procedures. And after that, people started to look then at, oh, well, there may be other reasons why a system can have an infinite state space, not only because it has recursive procedures, but there may be other reasons, like the process is actually multi-threaded program that can generate new processes, or maybe it is just manipulating the heap, right, and the heap can grow arbitrarily large. And for all those, automata theoretic techniques started to appear, okay? And if you actually look at which was the origin of this movement in the direction of infinite state systems, I think you can trace it back. This is an important paper in that area.
Have there been any attempt to move to the left?
Yeah, that was going to say, right? And the third impact that it had, this paper had, we have seen which impact it had here, which impact it had here, which impact did it have here. Well, automata theory had left quite a few big open problems open, right? And one of them was, for instance, the decidability of language equivalence for deterministic push-down automata. That was, you know, one of the holy grails of automata theory at that time. And these techniques actually have contributed a lot to the developments in that area. That problem was solved some years later by Jeroen Isserc. Okay, his solution was not using this, but actually, if you look at the developments after this paper appeared, a couple of years later, there was a Fox paper giving a polynomial algorithm for the language equivalence of so-called simple grammars. This was another holy cow of automata theory, maybe a little bit less than the decidability of deterministic, of the equivalence of deterministic push-down automata. And that was, it was shown to be polynomial by Hirschfeld, Jerome, and Moller in a Fox paper a couple of years later. So definitely that had this immediate impact. And then today, the best solution that, or the nicest solution that we know for the decidability of deterministic push-down automata is the one due to Colin Stirling, who is using techniques of coming from bisimulation equivalence. Okay, so actually this also had this impact in this direction, in that it contributed to solving some of the big open problems in automata theory. And yeah, so for me, what happened is that I moved to a postdoc in Edinburgh in '93, and there I was, people were very much aware of this, and actually a lot of things were happening in this direction there. In fact, Hirschfeld, Jerome, and Moller were there at the time, and I was learning, soaking this. I was trying to, I tried to work on that direction, on you know, proving decidability of bisimulation for something infinite, and I couldn't make any progress. I was not good enough. So then I decided, okay, let's think about model checking maybe, and I started to work in the model checking area. And that led a couple of years later to this paper about model checking push-down automata, which became relatively successful. And suddenly I found myself in a much more better position to do research expanding in different directions. So that's it. Thank you. Well, the proof is actually, you should not read this paper now. And the reason is that the proofs that they have there, they were using a kind of pretty graphical proof. When you look at the paper is full of pictures, right? And they are actually showing that you can, if you construct the graph of the configuration graph, right, where you are just saying, well, from X with an A, I go to YZ, and so on, you can construct a sort of tessellation, which is actually where you find the same, a finite number of pieces, which are repeated at different sizes, so to speak, but a finite number, right? And once you identify that finite number, then you can do it. But you shouldn't do that, because actually this paper immediately started quite soon after that. This paper, the people in Edinburgh started to work on it, and they found techniques which are much simpler. So in fact, the shortest proof that you have now is, which paper is that? I think the one by Jan Friso-Grote is probably the one with the shortest proof, and it's just a couple of pages. And what you do is just to find a finite basis for the bisimulation equivalence. Okay, so you know that you can find a finite base, and then from there you can generate all the pairs which are bisimilar. So that's the technique.
So you mentioned that the equivalence problem for two context-free grammar is undecidable.
Yeah.
But why, when we treat those variables in this grammar too, like a program in sequential composition, after that, then it becomes decidable? What is the magic?
No, the important thing is bisimulation equivalence. The problem is, okay, let me tell you a little bit more about bisimulation equivalence. If I find something to erase, it was hidden, right? Yeah, and in fact, let's do that. So the classical example of two systems which are language equivalent but not bisimulation equivalent is this one. Okay, so both systems can generate the same language, AB, AC, and the prefixes, right? So from that point of view, they are equivalent. But now think at what would happen if you would put them in parallel with a system which does an A and a B, okay? And imagine that actually what happens now is that these processes are communicating on these letters. This means that this process and that process, if they want to do an A, they have to do it together, right? So when you put it in parallel with this process, then what happens is that both do an A, right? And now this one can do the B. This one is willing to do a B or a C, and then they both will do the B and they will terminate, right? Now if you put it in parallel with the other one, right? They are going to do an A, but this process has no control about which A is this one going to do. And it might do the wrong one, right? So what happens is that now the process can block after the first A, which was not possible before, because this one, it can do this A, and this one will do this A, and now this one is only willing to do a B, this one is only willing to do a C, but they have to execute the same letter if they want to do something, okay? So then what you see is that, you replace something in the language view, you replace something by something that is language equivalent, but then you observe something that you didn't have before. But these two are not bisimilar, okay? And therefore, they are different things. And by similarity, what is taken intuitively, it is taken into account not only what can you do, but also at which moment, right? So, and which were the other options. So here the idea is that at this point you can choose between a B and a C, but here you cannot. And that's essentially the reason why they are not bisimilar. So bisimilarity implies language equivalence, but not the other way around.
I have two questions. So
Yeah.
One is, you pointed out very nicely the connection to verification. But intuitively, when you think of verification, interprocedural or concurrency, you think of intersection of two context-free languages. So, and we can decide it, but we'll replace it by a similar problem. Can you state this paper as somehow solving a limited case of intersection?
Well, it's definitely something that you can do. I mean, it's going to give you a sufficient condition, right, for language equivalence.
For deciding non-emptiness.
Right. And then what happens also is that, language... Oh, sorry, yes, I should have repeated the question. So the question was whether, that when you think about doing interprocedural analysis, program analysis, or something like that of in the program analysis area, you formalize this problem as the intersection of two contexts, deciding whether the intersection of two context-free grammars is empty, or to push an automata whether the intersection is empty.
Language as language, not intersection of languages.
Yeah, intersection of languages, right.
The
Yeah.
language of the control.
Yeah, the language of the, right. Exactly, and then whether this result could be interpreted as something that gives you at least a technique that you can apply in some cases, right? Well, the idea is that if you are able to show that two things are bisimilar, right, then in particular they are going to be language equivalent, and therefore you are going to be able to derive from this a kind of sufficient condition for certain for correctness of some programs. And the other thing which is important is not only that. The only thing which is important are the techniques that grew out of bisimilarity. Because of the following question. When your systems are deterministic, right, what happens is that bisimilarity and language equivalence coincide. Okay, and then what happens is that from the study of bisimilarity, you can define verification techniques. And then when you specialize them to the deterministic case, what happens is that you have language equivalence, you have techniques for language equivalence. And in fact, this has been very fruitful. For instance, that's exactly what Hirschfeld, Moller, and Jerome did in order to find this polynomial algorithm for language equivalence of simple grammars. They used the techniques that were coming from bisimulation, and then for these simple grammars, they are deterministic, right? They give you language equivalence. And the polynomial solution that they found was polynomial because they were using these techniques. They could prove then that there is a polynomial algorithm. The algorithms that were previously known, they were high up in the polynomial hierarchy.
So another question, perhaps less defined. Bisimulation is just one relation. I could think of some weaker form of relations. Then it would give me different mechanism of equivalence. Was they studied too?
So the question is whether, to say that the question is, well, you have language equivalence, you have bisimulation. These are two equivalence notions. And bisimulation is true that it is often very strong. The question is whether there is something in between, right? And yes, there were, well, at this point in 1990, there was an explosion of different notions of equivalence, which have survived the test of time. Well, there is one which has survived and which is very beautiful, and that one is testing equivalence. Testing equivalence, which is another way of, it is equivalent, or simulation, yes. Simulation is also, simulation is not an equivalence notion, but you can use it as a pre-order, yeah. Sorry?
Dick bisimulation.
And you can
Dick bisimulation.
The Dick?
Weak.
Yeah, okay, that counts as is the family, the bisimulation family, right? So you can also,
these are also useful to get some resulting verification, or this is like we found it, so you can also plug them and get some check for equivalence.
There are tools. Is it useful or not?
Yeah.
Take a small variation, for example, two-sided simulation.
Yes.
Which is different than
bisimulation, yes.
Is it decidable?
No, the idea is that by simulation, the idea is that essentially there was a whole hierarchy of equivalences between language equivalence and bisimulation, and only bisimulation is decidable. The things that lying in between, they were all no. So that was the magic of bisimulation, right? And the one that the important thing that this paper initiated. Yeah.
Sometimes by construction we give something that we know we preserve the simulation or the bisimulation relation, and also even though the building of the bisimulation might be polynomial, even high polynomial, then
Mhm.
conclude from whatever
Mhm.
trivial to the other one.
Right.
So,
Yep.
lots of applications
Yes.
in this direction.
You know, this paper, you can look at it in many different ways. You can look at it in the sense that it showed that by simulation was there was an algorithmic side to by simulation which was very interesting. But you can also look at it from a different angle and say, well, it showed for maybe one of the first papers that showed that it was possible to automatically verify infinite state systems, right? It also led to new techniques for interprocedural analysis, program analysis, and it contributed to solve long-standing open problems in automata theory, right? So actually I think it had a lot of impact, and it deserves, that's why I am claiming that it deserves more recognition than it has received.
But the paper, like the examples in the paper, are a bit boring.
Yeah, that's true,
And
yeah.
also the application that
Yes.
you give in the
Yeah, but look, for example, at the examples in Moshe's paper and with Pierre, right? I mean, do you have any examples? No.
All the examples are not boring.
Exactly, right? I mean, sorry to take it on you, right? But, you know, yes, that's true. I mean, but that's not, I don't think that's something that you should hold against the paper, right? The paper at that time, it really hit a nerve. But, you know, partially what happened is that soon afterwards, there came other papers that were actually giving much nicer proofs and much better techniques. And then this paper was not so often cited, right? Even though everything started there.
Because paper can be important in some sense for two different reasons. One, I would call by themselves, you know, paper that you still use, the algorithms you still use. This paper was important in the historical context because it was an important catalyst.
Yes, exactly. It was a catalyst.
The reason it is, I think, not so much cited today because it has done its service, so to speak. It's catalyzed.
Yes.
Probably some of the paper it catalyzed are not cited more.
Yeah.
But it was a very important catalyst.
Exactly.
In terms of influences people's career, yes, it was very influential paper. But it's outlived in some sense, you know, the children and the grandchildren are more important than that paper.
So when a student comes to you, you give him this paper or?
No. No. I mean, I give it as an important historical reference, and you know, you read the introduction and so on, but you don't read the proof because it's not. I mean, it's a very nice proof, right? But immediately, you know, it's very often the case, right, that the first proof is not the best proof.
But there is an interesting question here, which is if you look at, for example, all the results about model checking for context-free processes, they all can be now embedded in the automata theoretic context. I don't know about this result, how to do it automata theoretically.
No, I don't think, no, I don't know of any.
I don't know of
no,
anything.
I don't know of anything.
It kind of stand on its own in some
Yeah.
sense. It's its own specialized
Yes.
algorithm, even the simpler
That's
one.
true.
So
Yeah, so that's why I'm saying that something that was, I mean, that's how the paper influenced me, right? I didn't know how to do anything for by simulation, so I did it for something else.
The question still stands, can this be done automata theoretically?
Yes, that's true. That's still open. That's still open. Yeah.
So what should we read this paper? What is a good thing to read about this?
Well, as I said, if you want the best proof of this result, right, then the paper to read is, if I remember well, is a very short paper which I think appeared even in information processing letters, because at that point the proof was so simple that it could be written in 2 or 3 pages. If I remember well, the last version was one by Jan Friso Grote, so which is also a Dutch guy. But there were also intermediate things. I must also say that technically there are a couple of technical points. The proof in this paper was not was only for what is called the normed case. Is the case in which from every configuration you can terminate, right? And then it was later proof with a more complicated proof 1 or 2 years later for the general case, for the case in which you can also enter configurations from which you cannot terminate. But so then there is a little bit of reading there if you want to really get the technical proofs. But I think it is a good place to start. I should have actually looked up this. We can try to find it later. Yeah? I think it's an information processing letters paper.
More questions? Maybe ask more the 4 panelists to come and so on. Yes, thank you. Can you come up front? Go ahead. So,
And bow, you have to bow.
Okay, you have to bow. Good.
no, just want to thank you. I should say they actually.
So if you want, should we try? No, come on, come on. This is the way you do it, right? 1, 2, 3, 4.
They actually knew about this paper a few days ago and they prepared the slide yesterday. So thank you very much.
Okay. Good.
Thanks a lot.